Figured. I'd like to welcome Dr. Bar-Natan from the University of Toronto. He'll be doing a talk on car traffic and knot diagrams and some cool knot invariants. So please join me in welcoming Dr. Natan.
Thank you. So my title and abstract are on the screen, and I'm not going to read it out to you because I'm assuming that you've read them. I'll only say thanks for
inviting. Do you want those board lights off?
Sorry?
There's blackboard lights fading out your screen.
I don't know how to turn them off. Oh, but also,
There we go.
Okay. So thanks for inviting me to the CUMC. What I'm talking about is joint work with Roland van der Veen of Groningen. And the work was supported by NSERC and by the Chu Family Foundation. And everything that I will say follows a handout, so I hope you have a copy. And in full, it's on the screen right now. And there's also a URL, so if you go to that URL on the screen, you can get a copy of the handout, and later there will be a video of the talk, or a link to the video of the talk. And maybe I'll start, so really it's an aside. I want to talk about car traffic and all that, but the context is knot theory, so I need a brief introduction to knot theory. So I'm not going to formally define a knot. I don't know, a curve, map from S1 to S3, continuous, no self-intercept, I don't know, something. I'm not going to define. Here is one, okay? And it's considered the same as the one that you get by twisting it as much as you want, so long as the plastic tube doesn't go through itself. That's a knot, okay? There are lots of questions about knots. But in particular, just even telling them apart is hard. So, like, is it clear that this one is not the same as that one? So maybe intuitively it's clear, but you know, who knows? Maybe somebody one day will find a way to twist it in a completely crazy way, and then untwist it in another way, and show that they are the same. Well, no, we can prove that's not going to happen, but that's not entirely trivial. Likewise, there is the so-called trefoil knot over there on the left, and its mirror image on the right, and are they the same or not? And again, showing it is not exactly obvious. And in fact, if you want to know an example for how unobvious it is, you look at these two knots, and these two knots appeared in early tabulations of knots as different ones. And then in 1973, an undergrad, Ken Perko, looked at these and found that, well, they're actually the same. But it remains non-obvious. Like, you'll have very hard time seeing that they actually are the same. So we need tools, okay? And one tool is the so-called Reidemeister move theory and the so-called theory of invariants. So basically there is a theorem, which I will not prove, that says that knots are the same as knot diagrams, namely pictures drawn in the plane. Right? The knot itself is a three-dimensional Sorry. But it's a three-dimensional object, but you can project it to the plane, and then you get a planar picture, which is a graph with some obvious annotation on the vertices, like which side is up and which side is down. And a graph like that clearly represents a knot. And there is a theorem that says that two such knots are the same if and only if you can get from one to the other by a sequence of motions in the plane, which do not change the graph, and these Reidemeister moves. So if you have a kink, you can undo it. If you have like a, you know, well, whatever that is, you can again undo it. And if you have a crossing and a strand passing above the crossing, you can slide it down so that it passes below. And these are called the Reidemeister 1, Reidemeister 2, Reidemeister 3 move. And it's again a show that these two are the same by showing a sequence of Reidemeister moves like that. Okay? But how do you show that two things are different? For example, if you want to show that this is different than that, then what you do is you find an invariant. So an invariant is a function defined on knot diagrams, so defined on pictures of knots, and it better be, I mean, if you want it to be interesting, it better be relatively easy to compute and with values in things that are easy to tell apart. For example, numbers. Okay? So an invariant is defined on knot diagram, takes values in numbers or polynomials or matrices or something simple, in such a way that it does not change when you do any one of these moves. And then the invariant is just a function of the knot. And then if you compute the invariant on, if you compute your invariant on the trefoil and it comes out to be 9, and then you compute it on the circle and it comes out to be 3, and then you know that no sequence of Reidemeister moves will get from the trefoil to the circle, because the invariant does not change when you do Reidemeister moves, and this is 9 and this is 3. So you know that these two are different. So that's one of the things you want to do when you do knot theory, to find invariants. And that will help you to tell them apart. And then there are lots of other questions about knot theory. I don't want you to come out of here thinking that the only question is to tell knots apart. There are lots of other questions, but I'm not talking about them. Okay? End of introduction. Any questions, any comments? Yeah?
Could you give an example of the invariants?
I will, that's the point of the talk. So there are simpler examples than the one that I will give. You know, maybe I'll give the simplest example that I know, and it is, so if you have a knot diagram, you can look at the arcs of the knot diagram. There are 3 arcs here. 1, 2, 3, right? And you can color them with 3 colors. So say red, green, blue. And the question is, and you're asking yourself, how many colorings are there that have the property that in every crossing, either all 3 colors appear. So here red appears, green appears, and blue appears. Here also blue appears, red appears, and green appears. So either all 3 crossing appears, or only one, all 3 colors appear, or only one color appears. But never, you're not allowed, what is forbidden, verboten, is just 2 colors. Okay? So it turns out that this is an invariant of knots. And in fact, this knot goes to 9 because it turns out that there are 9 different ways to color it subject to these rules. And this one goes to 3, and that's why I chose the numbers 3 and 9 when I mentioned it before. But okay. But that's an invariant with integer values, so it's very, very limited, right? There are relatively few integers. It's very high. In fact, so it's a weak invariant. Like, for example, it will not tell apart the trefoil and the mirror image of the trefoil. Okay? Anyway, so end of topic, and let's move on to something else. So I want to tell you about how cars drive on knot diagrams. I should have said that my knots are always oriented. There is always a direction of flow. So when cars go on knot diagrams, they always follow the direction. They never go against the direction of the traffic. That would be extremely dangerous. You don't want to do it. And there are some additional rules. So when they go on an underpass, they just keep going through. But when they go on an overpass, then mostly they just keep going through. But with small probability, let's call it P, and in fact P is called 1 minus T. P is also denoted 1 minus T. With small probability, cars fall off from the overpass onto the underpass, and when they land on the underpass, they just keep going the same way. Like, they just keep going. Okay, so these are the traffic rules on knot diagrams. Here's a summary. So with probability T, where T is a number close to 1, cars pass through, and with probability 1 minus T, they drop down. And if they're at the bottom, they just stay at the bottom. Okay, there is another thing that you can have. You can have traffic counters. So a traffic counter, you know, you've seen them on the roads, right? These black strips that when you drive over them, they count how many cars go through. Okay, so here is another summary of the traffic laws. If you inject car traffic here, then the traffic counter placed here will measure T, or T units of traffic if you inject 1 unit, and a traffic counter placed here will measure 1 minus T. However, if you inject traffic on the lower strand, then a counter placed here will measure 0 because cars never jump up, and a traffic counter placed here will measure 1. Are the rules clear? I think they're sufficiently simple. I mean, yeah. Oh, maybe I went, okay. And the next definition is the traffic function. So the traffic function is really a matrix, G alpha beta, where alpha and beta denote edges of the knot diagram. And G alpha beta is the amount of traffic that a counter placed at beta will measure, assuming that you are injecting unit amount of traffic, I don't know, 1 car per second, on edge alpha. Okay? So again, it's a function of 2 edges, or a matrix if you wish. If you number the edges 1 up to something, then it's a matrix. And it's a matrix that measures, you inject traffic at alpha and measure it in beta. Okay? And just to be clear, if alpha is equal to beta, then the convention is that the injection point is before the measurement point. Otherwise, there is a 1 unit difference in the amount that you measure. Okay? And yet there is another comment. So strictly speaking, as stated, the answer is infinity, because, you know, if I inject traffic here, it will just keep flowing forever. Occasionally it will jump down, but it will just keep flowing forever. So if you place a counter here, it will count the same car infinitely many times, and so the answer will be infinity. So to prevent this, we cut our knots open somewhere, and basically put a cliff at the end. So the cars, when they reach here, they fall off and disappear forever. Okay, so we do this basically. The knots get opened, or the knot diagrams get opened. So let's do an example. Okay, so for the example, I'll use the simplest knot diagram I can imagine. It's not even a knot diagram. It's really just a single king, which by Bar-Natan 1 is equivalent to nothing, but I'm still talking about knot diagrams, not yet about knots. Okay? So I inject my traffic here, then a counter placed on that same edge will measure 1. Okay? Now, what will a counter placed here measure? So, it will measure 1, because any car coming from it, entering, eventually passes here. But then this car will go here, and with probability P, or 1 minus T, it will drop down and get counted a second time. But then with probability 1 minus T squared, it will drop down 2 times and get counted a second time, twice. And then with probability 1 minus T cubed, it will end up doing 3 loops around. So if D measures the number of times the car dropped at the interchange, then the total measurement will be sum of D greater than or equal to 0 of 1 minus T to the D, or sum of D greater than of 0 of P to the D, which by the, what is it called, the geometric summation formula?
Series.
It's 1 over 1 minus P, and our P is 1 minus T, so it's 1 over 1 minus T, so it's just T inverse. So a counter placed here will measure traffic amount of T inverse. Are we good? And then all cars eventually get here, and once they get here, they disappear, so they never get here twice. So a counter placed here will measure 1. Now, if you inject the traffic on edge number 2, then the counter here will measure 0. The counter here is the same. It just doesn't matter if you inject it here or here, because all the cars come here. So it will measure T inverse, and this one will measure 1. And finally, if you inject the traffic here, then this counter will measure 0, this one will measure 0 because there's just no way to go backwards, and this counter will measure 1. Okay? So the traffic matrix, or the traffic function, is the matrix 1 T inverse 1, 0 T inverse 1, 0, 0, 1, and it's written here. Yeah?
Is the matrix, does it depend on the cut?
The what? Yes, it depends. Well, does it depend on the node diagram? Or?
The cut. Like each cut is not open.
Oh, yes, it depends. It does depend on where I cut the node open. Yes.
So it depends on both the node and cut.
Yeah, it does depend on the cut point.
Okay.
Yeah. Okay. Well, that was a particularly simple example. Let's figure out the traffic function for a more complicated node. So I take the trefoil node. This is the trefoil node that you've seen before, and I cut it open, and I don't know. I hope this looks more or less like the thing on the picture there. And suppose I want to know, like if I inject traffic at 2, how much traffic will I measure at 5? Okay? And the answer is, it's complicated. Because you see, there are many paths to go from 2 to 5. There are several places where you could drop. And maybe this node is actually not the hardest because there aren't too many places where you can drop. But if you were looking at one of the nodes that were showing in an earlier slide, like there will be a huge number of different paths which could be repeated, and you could do path A, do a certain loop, then do path B, and do another complicated loop, then A again, then B 3 times. How would you measure how much traffic? How would you compute this? And the answer is, you call linear algebra, you call matrix theory, and matrix theory comes to the rescue. So here's how you do it. So let me just find, so instead of looking for how much traffic there is going from 2 to 5, I'll measure how much traffic there is from anywhere to 5. Okay? So if I inject the traffic at 7, how much will a counter at 5 count? The answer is 0. If I inject the traffic at 7, it immediately drops off the cliff and never gets counted. So G75 is equal to 0. Okay? Now, suppose I inject traffic at 6. How much will be measured at 5? Answer is, well, G65, the quantity I want, is equal to G75 because any car that gets injected at 6 flows to 7. Okay? So G65 minus G75 is equal to 0, and that's my second equation. Now, what about 3? So what is G35? So G35 is equal to T times G45 because cars that get placed at 3 with probability T go to 4. So G35 is equal to G45 plus 1 minus T G75 because with probability 1 minus T a car injected at 3 drops to 7. So I get the equation G35 minus T G45 minus 1 minus T G75 is equal to 0. And I get similar equations, so I get 2 equations from the yellow crossing, and 2 equations from the bluish crossing, and they are written here, and 2 equations from the pinkish crossing, but the 2 equations for the pinkish crossings are slightly different because the measurement point is near the pinkish crossing. So how is it different? So you see, if I was to inject the traffic at 5 prime, namely past the measurement point, then I'd get exactly the same equations as before. But my convention is that the injection point is before the counting point. So really I'm injecting traffic not at 5 prime, but at 5. So really, but you see, G55 is equal to G5 prime 5 minus plus 1, right? Because a counterplay, because if you inject the traffic before 5, then it counts 1 more than if you inject the traffic after 5. So the right-hand side of the equation that corresponds to injecting traffic at 5, instead of being 0, it's 1 more. It's 1. So this is a system of equations. And since we are masters of linear algebra, we know how to solve it. Namely, we set up a matrix. And here is the matrix. So I actually ordered the rows of the matrix according to the left index of the G that comes with a positive sign. So like this one becomes the bottom one, this equation becomes line number 6, this equation becomes line number 3, and so on. Okay? And then so you take this matrix and you multiply it by the column vector G15, G25, these are my unknowns. And the right-hand side is the standard basis vector 0, 0, 0, 0, 1, 0, 0. Okay? So how do you solve that? Well, the solution is that G alpha beta, in general, is A inverse applied to standard basis vector E alpha, and you measure entry number beta of the answer. Okay? So G alpha beta is just the alpha beta entry of the inverse matrix of the matrix A that I wrote here. And you type the matrix A into your computer, you hit inverse, and that's what it comes out to be. And so if you inject, what did I say? Inject traffic at 2 and read out at 5. So 2, 1, 2, 3, 4, 5. So that's how much traffic you're going to measure. Is it clear? Is this okay? Okay. Now, humans tend to think that this is horrible, because inverting a 7 by 7 matrix is like the most hellish exercise I could assign in a linear algebra class. Okay? But in fact, as I write here, computers don't care. And at the end, I want to do my computations on a computer. You see, in fact, solving systems of linear equations is computationally easy. Like there is this Gaussian elimination method, which if you do it as a human, you'll make a mistake and get the wrong answer, but a computer will not make a mistake and it's relatively fast. So in fact, you know, we're in easy universe still. Even though it looks ugly, we're in easy universe. Okay? Are we good? Can I move on? Yeah.
This is just actually a question from before. Is the convention that when it falls off like to the left relative to it?
No, it falls off and continue driving following the orientation.
But
Like
sorry,
the-
like which direction would it kind of fall off the overpass?
Either to the left or to the right.
Okay.
I mean, it depends. So like there are two types of overpasses, right? If this is the overpass, the road below could go this way or it could go this way.
Oh, okay, it just chooses the direction of the road.
Yeah.
Okay.
Yeah. Okay. Theorem. What's a theorem? So a theorem is a theorem with the t replaced by f, meaning instead of true, it's false. So here is a false theorem, but the point of theorems is that they are nearly true, or that they exhibit something that, you know, almost true, and if you only do a little bit more, you'll get it right. So bear with me and listen to the proof of the theorem, which will come after the statement. Okay? So the theorem says that the traffic function, well, you know, I wish I could tell you that it's a not invariant, but it's not a not invariant. It depends on at least three more things. It depends on where you've cut the knot open, and alpha and beta. Okay? So I'm not asserting it's a not invariant, I'll only assert that it's what I'll call a relative invariant. So, if you fix alpha, if you fix the edge alpha, and you fix the edge beta, so alpha is where you put traffic in and beta is where you measure it, then the traffic function is now invariant under Reidemeister moves done on some place away from alpha and beta, and also away from the endpoints, the cut point. Okay, so it's invariant under these moves when they are done away from the cut point. So basically, it's not an invariant of knots, but you know, if you had a like very complicated knot, if you hold your fingers at 2 points, the place where you inject and the place where you measure, and I suppose your third hand you put where you've done the cut, and you're allowed to move everything else, provided you hold with your thumbs those parts that are not allowed to move. Okay? Well, every theorem, as I mentioned, is followed by a proof. So here's the proof. So let me start with the hardest, namely Reidemeister 3. So here there are two basically this is the left-hand side of the Reidemeister move, and this is the right-hand side of the Reidemeister move, stylized in a slightly different way, but it's the same move. You see it, I hope. Okay. So now suppose I inject traffic at the bottom. What will I read? What will the traffic counters placed at the top read? So this car here at the bottom goes under, so it continues. Goes under again, continues, so this counter will measure 1. This one will measure 0. This one will measure 0. Likewise here. Here it takes a different path, but it still goes through 2 underpasses. So it will measure 1 here, 0 here, 0 here. That's the same. And the moral is that cars that go into a Reidemeister 3 interchange on the bottom right comes out with the same distribution, no matter whether it's the left-hand side or the right-hand side of the Reidemeister move. What about cars that enter that same interchange in the middle? So again, if a car enters here, then with probability t it will reach here, and 1 minus t it will drop off and reach here. Those 1 minus t cars will continue and exit the interchange here with intensity 1 minus t. The measurement will be 1 minus t. Those that get to here will continue to here and exit here with probability t. Okay? Likewise, on the right-hand side, well, on the right-hand side, you first pass through the first interchange, and with probability 1 you come here, and then with probability t you're here, with probability 1 minus t you're here. These two are the same, these three numbers at the top are the same, so if you enter in the middle, you'll exit on this with the same distribution, no matter whether it's the left or the right. Okay? Likewise, if you enter on the bottom left, this is the most complicated, and it actually requires high school algebra. So a car entering here will get here with probability t, and then to here with probability 1 minus t. And then to here it will get with probability t squared, and to here it will get with probability t times 1 minus t because it has to drop, and that's the numbers that you'll get at the top. On the right-hand side, it will get here with probability. You know what? Let me just do one of the measurements. Let's see how we can get here. There are two ways you can get here. One way is to go push through here and then drop and then flow, and the other way is to drop and then drop again. So if you drop and then drop again, you get probability 1 minus t squared. If you push through, you get here with probability t, then you drop and you get here with probability t times 1 minus t, and then overall the contribution is t times 1 minus t. So the overall probability of getting here is 1 minus t squared plus t times 1 minus t, and if you ask your high school friends, they will tell you that this is the same as that. And in fact, similar computations will tell you that this is the same as that, and this is the same as that. And therefore, the bottom line is, no matter where you enter a Bar-Natan 3 interchange, you'll exit with the same distribution, whether it's left or right, the left-hand side or the right-hand side of the Bar-Natan move. So basically we have shown that doing a Bar-Natan 3 move over here will not change G alpha beta, so long as this point, this Bar-Natan 3 is away from alpha and beta. Like inside the Bar-Natan 3 move, things get moved, get changed, but not outside. Okay? So, likewise, for Bar-Natan 1, we've already computed. If you enter a kink, you exit with probability 1. That's the same as just having an edge. If you enter, you exit. So Bar-Natan 1 does nothing, and our proof is nearly complete, except Bar-Natan 2 gives us trouble. So you see, if a car enters here, it gets here with probability t, and then it has to continue on the upper interchange, or upper lane, and it does it with probability t squared. But so I didn't even compute what this is. But you know, every car must exit. So if this is t squared, this must be 1 minus t squared. Not that I care, because it's anyway not what I would expect. If these two crossings weren't there, if it was the other side of the Bar-Natan 2 move, namely if it was just two parallel lanes, and I would inject traffic here, then I will be measuring 1, 0. T squared is not 1. I mean, most of the time. Okay? So, hence the theorem that I stated was false. But there is a resolution. And the resolution is to separate between the two types of crossings. So somebody before asked me about, well, in fact, there are two types of crossings. When you in a positive crossing, if you are looking up from the underpass, the traffic you see above you moves from left to right. In a negative crossing, if you are looking up from the underpass, the traffic you see goes from right to left. Basically, Canada versus England. Okay? So this is in fact a positive crossing, because you see, if I was looking down from the underpass, meaning from the other side, then the traffic would seem to go from left to right. And its mirror image, again, if I'm driving into the crossing, and I'm looking up to see how the traffic goes, it seems to go from right to left. Again, I'm coming from the other side. So, so that's an English crossing. And then the trick is to change the traffic rules, and the probability for dropping, instead of being 1 minus t, on negative crossings, it becomes 1 minus t inverse. This doesn't change anything in what I've done before, because all of these crossings were positive. However, in the Reidemeister 2 move, one of the crossings is positive and the other is negative, so something does change. And in fact, the change is that, okay, this is a positive crossing, this is a negative crossing, and if a car comes from here, it continues with probability t, and then it continues again with probability t inverse, but it only got here with probability t, so t times t inverse is 1, so it gets here with probability 1. And then this has to be the complementary number, so it's 0, and that's what we get over there. And there is small print, there are other lane orientations that must also be checked, meaning maybe you reverse one of those lanes, and you still have to check that. Everything checks. Okay, this is just mechanical check. Okay? And then there is the bigger small print, and the bigger small print is what? T inverse, if t is a number between 0 and 1, t inverse is bigger than 1. So there is no such thing, probabilities bigger than 1. And what about 1 minus t inverse? That would be a negative probability. I don't know what that is. Okay? So you see, maybe I'm not really a mathematician, but I'm an algebraist. And algebra doesn't care. So basically, when I talk about probability theory, call it, if you wish, algebraic probability theory, I don't care. I will never use inequalities. I will never use interpretations as in which you talk about frequencies, in which you talk about out of 1,000 trials, how many times something happened. Okay? However, I will use the algebraic rules of probability, and I have used the algebraic rules of probability. Namely, if you have two disjoint events, the probability of their union is the sum of their probabilities. Hey, where did I use this? I think I used it here. The probability of getting here was the sum of two disjoint ways of getting there. And the other rule that I will use is that if you have two independent events, the probability that they will both occur is the product of their probability. And I've used that too, namely the probability of passing through once is t, and then the probability of passing through the second time makes it t squared. Okay, so these are the only, this is algebraic probability theories. That's the only rules that I'm allowed to use. I've used them and I'm not allowed to use anything else. But the theorem became a theorem. Okay? So I have this theorem and everything okay? Good. Okay, now comes the real hard stuff. So, okay, so that same matrix that I wrote before, call its determinant delta, and actually its determinant you have to multiply it by, you have to renormalize it, so you have to multiply it by some power of t, and I mean, I will not tell you how to determine this power of t, I will only tell you that it's easy. It's in fact easier than what we've done so far, but I just don't want to move in a different direction. Okay? Then, here is a function of crossing. So if you have a crossing is determined by the edge, the incoming upper edge, the incoming lower edge, call them I and j, and by a sign which can be plus or minus. So I define a function of crossings, let's call it R1 of C, and the function is this horrible mess. So basically, S times GJI times GJ plus 1J, blah, blah, blah. I don't know, some horrible mess. And then I define rho 1 to be delta squared plus times the sum over all crossings of R1 of C plus a minor correction. Again, I'm only telling you that there is a minor correction so that you will not tell me that I'm a liar. But the minor correction really is minor, and I just don't want to waste time telling you about it. There is a second contribution that has to do with the times when an edge rotates. So some edges are more or less straight, and some edges make a rotation, and you have to count these slightly differently. But it's really minor, and I don't want to waste time on this. Anyway, the theorem, and this is a theorem, not a theorem, is that both delta, defined above, and rho 1, defined here, are not invariants. What is the proof? So again, I've limited time. I'm not going to show you the proof. I'm also only going to tell you that it's relatively easy. Basically, how is rho 1 defined? Basically, you sum over crossings, and the summand is some combination of traffic functions that begin and end near that crossing. So now suppose I do a Reidemeister move here, it's not going to change the summand coming from this crossing. So the only summands that are going, and that's because of the first theorem. And so the only summands that will change are the summands where the Reidemeister move is touching the crossing being summed. Right? I sum over all crossings. So if I do a Reidemeister move, the sum will include the crossings that are at the Reidemeister move itself. So there are so of this sum, 3 of the summands may change, and it's a relatively minor algebraic analysis to show that at the end it doesn't change. Again, I'm not going through it, I'm only telling you that it's easy. And then comes theorem 3, and theorem 3 is the same but harder. So you let T1 and T2 be 2 variables. Instead of 1 probability, T, you now have 2, T1 and T2. And then let T3 be the product of T1 and T2. And now I have 3 traffic functions, G nu alpha beta, where nu can be 1, 2, or 3. Namely, the old traffic function, but with T replaced by T nu. Okay? Likewise, I have 3 determinants, delta nu, namely delta with T replaced by T nu. And then I have a function of a single crossing, and it's lovely, and it's written here. Actually, no, you should say it's horrible and ugly, but I never do these computations by hand, and computers don't care, okay? So it's a function, it has 18 terms, or maybe 14, I don't remember. That's way more than what I can handle, but for my computer, it's just nothing, okay? And likewise, there is a function f2 that depends on two crossings, C0 and C1, and again, it's written here using an obvious notation. Okay? So, the claim is that if you define theta of d to be the sum of f1 over single crossings, plus the sum over pairs of crossings of f2, plus a minor correction, which again is minor, and I'm skipping it because of interest of time, the claim is that this is a not invariant. And in fact, delta remains a not invariant, so the pair delta comma theta, which I will call uppercase theta, is a not invariant. One word of interpretation, like the two-term, the double summation term, kind of measures if you have measures how much traffic you can make that where like traffic starts near crossing number 0, goes with car number 3, with car whose probability law is determined by T3, to crossing number 1, and then the car kind of breaks up into two cars, car 1 and car 2, which go back to crossing number 0. So it's kind of how many theta graphs you can put on your node diagram, theta graphs of traffic. Okay? And that's what gives the invariant the name. And it's also gives the invariant the relationship with physics, because these are closely related to Feynman diagrams. Anyway, I'm not going to tell you the proof. I'm only going to tell you that the proof is, again, an easy computation. Basically, mostly it's obvious, and the one issue is if the summations are near the crossing, and then it's a little calculation. Now, again, this may seem horrible, but it's actually super fast. So people may be aware, actually, you know, let's start with the invariant I mentioned here. So this counting of coloring, it was so easy to define that I defined it, you know, on the spot without preparing anything. However, if you have a complicated knot and you want to count how many colorings it has, you have to go through all of the arcs and assign each arc a color and decide whether it's a legal coloring or not. And it's a priori an exponential amount of work, because the number of assignments of colors to the arcs is exponential in the size of the diagram. Likewise, if you know the Jones polynomial as defined by the Kaufman bracket, so it's defined by the relation a crossing goes to A times a vertical smoothing plus A inverse times a horizontal crossing, smoothing, sorry. And it's so easy, it's one line. But really, you have to apply this relation to all crossings. So if you have 100 crossings, each crossing you have to either convert it to or you have to sum over all ways of each crossing, either convert it to a vertical smoothing or a horizontal smoothing. That's 2 to the 100 operations before you've done anything else, okay? So it's actually very hard to compute. But our invariant is inverting a matrix, which again, human horrible, but computer easy, and then a double summation. A double summation, if you have a knot with 100 crossing, a double summation takes 100 squared operations. 100 squared is 10,000. It's nothing. Okay, so in fact, this invariant is super fast to compute, even though it's ugly. Furthermore, it's super strong. So here is a table with there are 249 nodes with up to 10 crossings. Never mind how they were enumerated. And in fact, before Perco, there were 250, and then Perco found a mistake. But these numbers are modern, done by different techniques, and they're solid. Okay? If you're looking at knots with up to 15 crossings, there are 300,000. If you're looking at, here is a list of standard knot invariants that are relatively easy to compute, though still harder than theta, way harder than theta. Okay? So it's the Helmsley polynomial, Chovanov homology, the hyperbolic volume, and the Levin-Tristram signature, whatever these are, okay? Again, they are harder to compute, and here's what they give you. So for up to 10 crossings, you get 249 distinct values from taking this list of invariants. So this list of invariants, just as a 5 tuple of quantities, no, 4 tuple of quantities, gives you 249 crossings, so the deficit is 0. They separate everything. If you look at crossings with up to 11, knots with up to 11 crossings, you get 787 values, which is less than 801, so you have a deficit of 14. So the bigger the deficit is, the weaker your invariant is. And when you go to 15 crossings, you get a deficit of 40,000. However, theta has a deficit of less than 7,000. And if you take everything together, the deficit drops a little, but not a lot. So basically, theta seems to be as strong as all of these other, well, stronger than all of these other things taken together. Okay? And it's much easier to compute. Another nice thing about theta is that it's fun. So again, not the formulas, the results. So let me tell you, here is a gallery of values of theta. So theta is a pair. Uppercase theta is a pair, because to compute theta I had to compute delta, the determinant of A on the way. So may as well keep it. So delta and lowercase theta. Delta is a polynomial in one variable. Theta is a polynomial in, namely t. And theta is a polynomial in two variables, namely t1 and t2. Now, a polynomial in one variable, it's actually a Laurent polynomial because inverses are also allowed. But anyway, a polynomial is just a list of coefficients, and you can turn a list of coefficients to a barcode. Basically, the positive coefficients become red bars, the negative coefficients become blue bars, and in fact, you make the intensity be proportional to the size of the coefficient. So, if you look at the 300 crossing knot, this is huge. I mean, it's so huge that I cannot print it. Okay? But if you look at the random 300 crossing knot and you compute its delta, you're going to get a polynomial of degree, what is it? I don't know, 100. Which looks like, and if I wanted to show it, I would just display a barcode. And that's the barcode that you get. Fades out at the end, and sort of solid red and blue in the, red and blue in the middle. That's not terribly interesting. That's delta. Delta, I should say, was discovered about 100 years ago. Theta is the new stuff. However, okay, theta is a polynomial in two variables. A polynomial in two variables is basically an array of coefficients. Instead of a row of coefficients, you have the coefficient of t1 to the i, t2 to the j. You call it aij, so you get a two-dimensional array. So instead of getting a barcode, you get a QR code. Okay, or you get a picture whose pixels are determined by the signs and magnitude of the coefficients. This is the picture you get for theta for a 300 crossing knot. By the way, 300 crossings is kind of science fiction for other invariants. Like the mere fact that you can compute something for 300 crossing knots is amazing. But anyway, this is the picture you get down here. But if you look at this picture, you see that there is a hidden hexagonal symmetry. Namely, if you shear this picture, so if you take the top edge and you slide it to the left, and you take the bottom edge and you slide it to the right, then the picture becomes the picture here, which is a perfect hexagon. And by the way, I still don't know how to prove that you get perfect hexagonal symmetry. You get perfect hexagonal symmetry, the formulas don't explain why, but you get it every time. Okay, yes?
Would you expect it to be symmetric, like matrix?
It is, but I don't know why.
Okay.
I basically know nothing about this symmetry. Okay? Well, I wouldn't say I don't know. I mean, the invariant has a history. It came from somewhere, but somewhere, and somewhere in the early history it would have been clear, but at some point it lost the connection with the history. So at the end I don't know how to prove it. Okay? Anyway, here are a few other examples. So these are random notes with fewer crossings, and I've only displayed the hexagon part, not the barcode, because the barcode is boring. You can see do you know these pictures that you get when you put sand on a drum and then hit the drum, and then you get kind of diffraction or, I don't know, patterns. It's called Keladny patterns. Okay? It looks like that. I have no idea why. Okay? Then, however, for some other knots, so this is the so-called 241 minus 41 pretzel knot, whatever. There are two twists here, 41 here and 41 here. So it's a knot with what, 84 crossings, I think. And about, give or take, okay? And here's the picture you get. It has hexagonal symmetry, but it's not a hexagon. Here are a few torus knots. So the knots are displayed here. They're called torus knots because they can be drawn on the surface of a torus. I have no idea what's going on. And finally, here are the first 249 knots. The two that correspond to the Perco pair are roughly this one. Sorry, the one that corresponds to the Perco pair is roughly this one. But again, there are lots of patterns here. I have no idea what they stand for.
What do the blanks represent?
The what?
You have some
Oh,
empty.
so the blanks represents notes for which theta is actually 0. And, but then the barcode is not 0. And so actually early on, there are a few examples where theta is 0. For big knots, it's actually never, it rarely happens. So it's kind of it's a small knot coincidence. And then in that small knot coincidence, we get saved by the barcode. So in fact, each of the squares here has a different picture in it, though sometimes it's hard to tell. So like, I don't know, if you compare, I don't know, some of these pairs differ only by a tiny amount of red shade. Okay, so, you know, my printer is not good enough to tell.
On my size, it's really hard.
Yeah, well, okay. But again, okay. So I'm close to the end. So the morals are matrices are useful, linear algebra is cool. Two, there is some probability theory, not quite probability theory, but some sort of probability theory outside of the interval from 0 to 1. And the last one is that there is still a lot that we don't know, even at the level of very basic mathematics, matrices and the like. Now, if you want to read more, there is an article in Quanta magazine based essentially on this talk. There are some videos and handouts from many other talks that I've given. Some of these are much deeper, like tell you about the relationship with quantum field theory, with quantum groups, or whatever else, at this URL. And finally, the original paper with Roland van der Veen with some more contacts than actual proofs and code is at this URL. And thank you for inviting me to this. it is known that the answer is no.
Oh.
Namely, there's some operation called the Whitehead double, and it's known that if you start from any knot and do the Whitehead double twice, then it has the same theta invariant as the unknot. And I lied to you. It's only known at the level of a conjecture, but it's a conjecture which is kind of solid. Over there, I don't know. Yeah.
If graph theorists were interested in something like this, are there any like past attempts to parameterize things like knots and for like problems of this nature? Or that you know?
Sorry, I'm not sure I didn't understand.
Yeah, sorry. Have there been like I just via knot diagrams sort of just made me think of like potential graph theoretical like applications, like some overlap in these two studies. I was wondering if there's any attempts like that in the past, I guess, that you know of.
I mean, there is tons of relations between knot theory and graph theory. Most of them completely untouched by what I talked about today.
Yeah.
Yes, but you're opening a huge discussion.
Actually, yeah. Thank you.
Yeah.
In the actual research, as you were originally doing the research that led to the paper, were you thinking about this traffic explanation as how you were coming up with it, or was that a thing you kind of came up with after the fact?
No, that came up later.
Okay, as a tool you
So,
had to
in fact, the history, often the history of mathematics is, not quite as, telling it in a class is not the same as how it was discovered. So, it would take me much longer to actually describe the history, but basically, in some sense, it started from quantum field theory and then moved on to finite type invariants and the so-called loop expansion, and then quantum algebra and quantization of Libby algebras, and like a whole lots of different things. And then at the end, we found that there is a simple interpretation of many of the things. However, that simple interpretation does not explain the ugly formulas. So, I mean, these are formulas that I just told you. Here are the formulas. One of the big questions is to find an explanation to these formulas in a language which is as simple as the explanation for the primary ingredient, meaning the traffic function. Yes?
It does. I noticed that you said that in Theorem 2 we showed that, or we didn't show, we kind of proved that row 1 is also a knot invariant. And I was wondering why you didn't include it in big theta. Is it because small theta just
As it turns out, and in fact there is a recent archive paper on it by a student of mine, it turns out that theta dominates row 1. So if you take theta and substitute one of the variables to 1, then it becomes a polynomial in one variable instead of 2, and it is row 1. Yes?
Do you know if there's any work in trying to find knot invariance using maybe A1 homotopic methods?
Sorry, A1 homotopic?
Like motivic homotopic methods?
I'm not exactly sure what you mean, and it's over my IQ. But maybe I'll just say that, maybe I'll tell a little story. So, when I was a graduate student, I was studying mathematical physics, and I was looking down at knot theory. Knot theory is silly. I mean, it's pictures in the plane. I mean, there can't possibly be an interesting theory of knots. I mean, and I was wrong, and it's a bit, and at the end it turns out that knot theory is more like number theory. So numbers are also silly. I mean, who cares if 27 times 29 is equal to whatever it is, 600 something, I don't know. Okay, who cares? Okay, and the reason people care is because when you ask questions about numbers, they end up forcing you to think about a zillion different topics in mathematics, from I don't know, arithmetic algebraic geometry to Riemann-Zella functions. Okay, and knot theory is kind of the same. So I mean, it looks silly, but it ends up connecting to everything. So pick your favorite topic, it's connected, even if I don't know how. Yes?
The Rolston table, does it start at 3-1 or the unknown?
3-1.
It starts 3-1, okay.
With the unknown, it's 250.
Okay, okay. Then if I can count, which is, 4-1 and 6-3 seem to be the first ones where theta vanishes, and those are also the first two amphichiral knots. Is there any kind of connection there that you would think?
Conjecture theta vanishes on amphichiral knots.
Cool, thanks.
Yeah, that's one of the many things that are not apparent. If you look at the formula, it's not clear why it should be so, but it is so. Yes?
Is there a particular reason why the probability the car crosses the bridge is chosen to be close to 1 and not sort of arbitrarily chosen?
Oh, it's not close to 1, sorry. The word close to 1 is in fact meaningless in my language because I'm an algebraist. Okay, or at least I'm an algebraist for the purpose of this talk. Okay? and I only said it for the intuition. The intuition is that at the end everything goes through. Like for example, when I did the kink, I said this comes out 1 because at the end everything must come out. But it's not really. It could have been done by a calculation. Yes.
Is there any connection between this invariant and the Linskold invariant?
Not that I know.
Okay. Yeah, it just resembles it in...
There are several ways that they resemble each other, but I don't know a connection, and it's not even that I don't know how to prove a conjecture, I don't even have a conjecture.
Okay.
Yes?
Does it also work for links?
With some small print, yes. So, yeah, with some small print. I could, yeah. And people who know about virtual knots should ask, does it work with virtual knots? The answer is yes, with some small prints. It has to be rotational virtual knots, not ordinary virtual knots. And you lose the hexagonal symmetry. Yes?
Wait, on that element, what goes wrong if you drop the rotational assumption on the virtual knot?
It's not invariant.
Like what goes
I
on?
mean, not in the not
goes wrong in the
not
argument?
like NOT, not knot.
Yeah.
Sorry.
Like what goes wrong in the argument?
You try to run the argument on I mean, I didn't tell you what the correction was.
Yeah.
Right? When I gave the formulas, I said, here there is a minor correction. Where did I? Here. There is a minor correction. Without the minor correction, the correction is minor, but without it, it's not an invariant. And the correction has to do with places where there is a rotation. And that's exactly what virtual knots do.
Yeah.
They allow you to talk about where there is a rotation, even though it's just virtual. Nobody's telling me to